All right, class, welcome. So, you've got the hang of the big three in electric circuits: voltage, current, and resistance. But all that theory really comes to life when you flip a switch. And that's what we're tackling today: the crucial concepts of energy and power. Mastering Ohm's law is essential, but it really only tells part of the story. The really interesting stuff, the part that makes a circuit do something, like light up a room or turn a motor, that all comes down to how circuits use energy. And this fourth quantity, power, is the absolute key to unlocking that. This is where we move from just theory to building things that actually work. Okay, first things first, let's get our definition straight. When we talk about energy, and we'll use a W for it, we're talking about the fundamental ability to do work. Think of it as the raw potential, the fuel in the tank. We measure it in joules. Now, this is where it gets really important. If energy is the fuel, then power is how fast you're burning that fuel. Your car's gas tank holds a certain amount of energy, right? But the engine's horsepower tells you the power, how quickly you can convert that fuel into motion. It's the exact same idea in our circuits. Power is all about the rate. And this leads us to a beautifully simple fundamental relationship. Power is simply energy divided by time. P equals W over T. So if you use 1 joule of energy over the course of 1 second, that is, by definition, 1 watt of power. It's that straightforward. The watt is our yardstick for measuring how fast work is getting done. So we've got the general idea down. But now, let's connect this theory to what's actually happening inside the wires and components. What does power physically look like in an electric circuit? Take a look at this diagram. Inside that resistor, there's a constant microscopic traffic jam. As the electrons, our current, try to push their way through, they're constantly colliding with the atoms of the resistive material. And every single one of those collisions transfers a little bit of energy. That energy has to go somewhere, and it escapes in the form of heat. That steady release of heat, that's power dissipation in action. And that very physical process gives us our most fundamental formula for power in a circuit, sometimes called Watt's law. The power being dissipated is simply the voltage pushing the electrons multiplied by the current, or the flow of those electrons. P equals V times I. This is your foundation. Write it down, memorize it, it's the bedrock. But what happens if you're in a situation where you don't know the voltage? No problem at all. This is where Ohm's law becomes our best friend. We know that V equals I times R. So if we just substitute I times R in for V in our main formula, we get a second incredibly useful tool. Power equals current squared times resistance. P equals I squared R. This is your go-to when you have current and resistance. And, we can play that same substitution game again. What if you know the voltage and the resistance, but you don't know the current? Well, Ohm's law tells us I equals V over R. We just plug that into our base formula, and we get our third variation. Power equals voltage squared divided by resistance. And there you have it, a complete power toolkit, 3 formulas to handle any situation. Now, theory is one thing, but let's actually put these tools to work. We're going to run through a few quick examples. And the real skill here isn't just knowing the formulas, it's about looking at a problem and instantly knowing which tool is the right one for the job. Okay, look at circuit A. What are we given? We're given a voltage of 10 volts and a current of 2 amps. We have V and we have I. Well, this is a no-brainer, right? We grab our first formula, P equals V times I. Plug in the numbers, 10 times 2, and that resistor is dissipating 20 watts. Done. All right, now let's look at the second circuit, circuit B. This time, the problem gives us a current of 2 amps and a resistance of 47 ohms. No mention of voltage. So the most direct path to the answer is P equals I squared R. So we take 2 squared, that's 4, and multiply it by 47, which gives us 188 watts. See how easy that is when you pick the right tool? And for our last example, circuit C. Here we've got 5 volts and 10 ohms. They give us voltage and resistance, but not current. So we reach for our third tool. P equals V squared over R. That's 5 squared, which is 25, divided by 10, and our result is 2.5 watts. Picking the right formula makes the problem almost solve itself. Okay, let's flip the script a little bit. These formulas aren't just for finding power. With a little bit of basic algebra, we can rearrange them to find any of the other variables. And this is something you'll do all the time. Let's use a classic light bulb example to see how. So here's a very common real-world scenario. You've got a standard 100-watt light bulb, and you plug it into a 120-volt wall outlet. The question is, how much current is that bulb actually drawing from the wall? We start with our fundamental formula. P equals V times I. We just need to solve for I. So we rearrange it. I equals P divided by V. Then we plug in the numbers we know. 100 watts divided by 120 volts, and we get about 833 milliamps, just like that. So let's wrap this up. What do you absolutely need to remember? First, power is the rate of energy consumption, measured in watts. Second, you now have this indispensable toolkit of 3 core power formulas. You've got P equals VI, P equals I squared R, and P equals V squared over R. Your job is to look at the circuit and pick the right one based on the known values. Master that, and you've mastered the fundamentals of DC power. But this brings us to a final and frankly critical question. It's a question that every one of you will face as soon as you start building real circuits. We just calculated that a resistor might be dissipating, say, 2.5 watts. But can it handle that? What if that little resistor is only designed to handle half a watt? It's going to burn up. This is the crucial topic of power ratings, and that's exactly what we're going to dive into next time.